Hi, I haven't forgotten about this little project over here, the Elliott Sound Products guitar preamplifier and the ElectroIndia N-channel amp. I just need to do one little thing. Greetings, the Astro 30 here yet again, and I want to touch on this ElectroIndia power amplifier that I got in that aluminium box over there, and the Elliott Sound Products preamp that I got sitting next to it. I haven't forgotten about it. I haven't forgot about the speaker box that it's sitting on top of. I've just had other things going on in the background, and yeah. I have made a decision though. I am going to use these two Sonar transformers, 30 volt, rather than buying a toroidal. And there's just one thing I need to add to that amplifier to make it a little bit more complete. Now, the power amplifier itself does not make a thump, but when it's connected to the preamp, well, yeah, it does. There's no turn off transient as far as I know, but there is a turn on one. So I'm going to need a muting relay. Now, I could use the Elliott Sound Products loudspeaker protection and muting circuit, but he uses an off-board relay for that. There's no on-board relays on the PCB that he's manufactured, so I want a bit of a more elegant solution. Now, I don't really want to detect and protect against DC on the output. It's not really a concern of mine. The speaker that's in that box is a piece of crap anyway, so it doesn't really matter, it's not expensive. But I'm going to add to the power supply a little muting circuit down here. Now, for those of you that are as old as I am, which is over the age of 40, you might recognize this circuit. And I'll give you a few seconds to think about it. This is actually the power supply circuit that was designed for the ETI 480 amplifier, the 50 watt and the 100 watt version, which was released in March of 1977, the year of my birth. 2 months before I was born, but okay. Okay, and here is a redrawn version of the schematic from the whiteboard, so it's a little bit more clearer to understand. We're going to ignore the power supply section up here because it's not really relevant to what I'm going to be discussing. That just produces a high current BCC rail, as well as giving you the bipolar ground connection. It's pretty much well stock standard linear supply. I will say one thing about it though, is the max AC voltage should be 60. Let's try that again. The max AC voltage that should be applied to this circuit should be 60 volt center tapped, or 30-0-30. Any higher than that and I cannot guarantee that this circuit will function properly. Oh, that stinks. So anyway, we'll look down here at the de-thump circuit. Now, excuse me for the flatulence outburst there, but anyway. So up here we've got a half-wave rectifier coming off of one end of the transformer, which is just out of shot, which then gives us a positive VDD line here, which is what I'm going to call it. And then that goes to this 47 microfarad 63 volt capacitor to provide a little bit of filtering. Now, as this is half-wave, we're only going to see about half the voltage of that side of the transformer. So that side of the transformer is, say, 30 volt. We're going to see 15 volt at this node here, and with this capacitor basic filtration there, we're going to see roughly a voltage of 21 volt here at this node now, DC, and that's because we're applying the RMS rule to the value, which is multiplying the DC voltage by the square root of 2, which is 1.414, to give us our actual DC voltage. If this capacitor wasn't here, then you wouldn't apply that rule. It would still be 15 volt DC unfiltered. Now the reason this capacitor is here is to stop this relay from chattering, because there's going to be ripple through this circuit, so the relay may chatter. There's also a 2K2 resistor here going off to a connector to ground for an LED. I've included this so it's a handy little connection for a panel LED indicator to tell you that the power supply is on. And it can also drive one of those panel switches that uses an LED to illuminate the switch. This resistor is subject to experimentation and change. If the LED brightness is too low, decrease the resistor. I've only put that there as a basic safety margin to stop blowing up like high intensity LEDs and stuff. And that capacitor there also stops that LED from flickering. I mean, it's not that visible to the naked eye, but through a camera it is definitely visible. Over this side we've got a 47K resistor which goes to the positive VCC rail up here, and then that goes to this other 47 microfarad 63 volt to ground. This forms an RC network. Now that's a time constant, and with these values here that gives us roughly a turn on delay time before we reach 0.6 of a volt here at the base of this transistor of roughly 2.2 seconds. I'm going to say 2 seconds rounded. So then that provides the slow turn on base voltage for this BC548. Now at the voltages we're using, the collector and emitter voltage is maximum is 30 volt on this transistor. I would consider using a BC546 or BC547 respectively, because the 47 has a 45 volt collector emitter voltage. Anyhow, the collector is connected to the half-wave rectifier, so this half-wave rectifier is also supplying the collector current for this transistor. Now when the power supply is disconnected, that means the current flow through the transistor is instantly turned off, instantly dropping the relay out with, you know, a few milliseconds delay. The emitter is then driving this 470 ohm dropper resistor, which I'll explain in just a second. The original circuit did not have this 1N4004 flyback diode across the relay coil. Now, when the relay coil de-energizes, it can send over a 500 volt spike voltage back EMF, and the first place it's going to go is through the transistor. Because of the placement of this relay is on the emitter circuit, it's most likely going to find its way to ground. But to stop the spike as much as possible, that suppression diode is put there just as a safety margin. And the contacts of the relay are connected to two connectors. One's the speaker out, which comes off of the normally open connection, and the amp in, which goes into the center or the common pin of the relay. Now as you can see, I'm only using a single pole dual throw relay. The reason for that is that in a stereo amplifier you really should have two separate power supply transformers for each channel, so you can reduce the crosstalk across them. Plus also I'm only using this in a mono amp, so I only need a mono input. Plus it makes routing the PCB a hell of a lot easier. So that's about all I can say about the circuit. However, back to this resistor. That resistor value is calculated by the formula of the VDD line minus the coil voltage, so you need to know the coil voltage, divided by the coil current. Now the relay I'm using doesn't tell me the coil current, but it does actually tell me the DC resistance of the coil, which is around 270 ohms. So using ohms, yes, we can calculate what the current is of that relay. Okay, so to work out the current, it's the voltage divided by the resistance. So it's a 12 volt coil divided by 270 ohms. That gives us a current of roughly 44 mA, which is fine. So now if we apply the formula of VDD minus the coil voltage, which is 21 roughly, minus the coil voltage divided by 0.044, so our VDD is roughly 21 minus the coil voltage, that gives us 9 divided by the current, gives us a resistance value of roughly 204 ohm. I would use 220 ohm, However, 470 did actually work fine in that circuit, so for now I'm going to leave it alone at 470. And the final bit to this equation is to work out the wattage of the resistor, like what wattage you should use. It is the coil voltage multiplied by the coil current. So it's coil voltage multiplied by 0.044. That gives us roughly a little over half a watt. So a 1 watt resistor is a must here. Alright, so that's the schematic explained here. There's not much more to talk about with it. Now, all I need now is a relay, a couple of resistors, a couple of capacitors, and maybe an LED or two. And yeah, then we can actually get started in actually testing this, but I don't have them right now. Random stuff keeps appearing on my desk. Okay, and I now have a relay. However, it's smaller than they used to be. They used to be a little bit taller than this. Some were clear, kind of tiny, but that should be alright. It's 12 volt, 270 ohm coil. It's actually a Panasonic one. I always thought they were Omroms, but okay, so there's a relay. I've got a bunch of resistors I'm going to need for the circuit, 220 ohm and 470 ohm 1 watts, because of that calculation that I explained before, and plus 47k half watt resistors that I don't have, now I do. And a
full bridge rectifier.
The only reason I bought this was because I wanted to double check my pin spacing for the PCB. I'll tell you a story about this. Originally, when I laid the PCB out yesterday, I used a footprint which matched this. Then I looked on JCar's website and actually downloaded the datasheet for this. And the pin spacings contradicted to what I could see in the picture and the footprint that I was using. They wanted like 7.5, 7.6 between pins. And they had like larger areas up here. And I thought, oh well, I'll change my my layout and re-upload the Gerber file. And made my own footprint because KiCad doesn't come with it for that size. And then so I did that. That was all fine. And I bought this today and realised the original footprint was right. So I'm going to have to change the thing again and re-upload the Gerber file. Anyway, this is a KBU 604. It's a 400 volt 6 amp bridge. Well, that at least is what it says it is. But it looks pretty hefty. I mean, the size of these pins, they're like 1.5 millimeter. There is another part number on it. It says GW741, so it's either KBU 604 or GW741, if you want to cross-reference that. Okay, so there's my full bridge rectifier. I've got a couple of 47 microfarad capacitors here. Now I wanted the normal RB ones, but JCar only had one, and I needed two. So I went with the more expensive version, which is the low ESR ones. Whatever, they're 50 cents versus 46 cents. And a couple of red, I think they're 40 MCD LEDs. I bought two because the likelihood of me blowing one is pretty high. So with all these parts now, I'm going to have to build up the relay de-thump circuit, is what I'm going to call it, on breadboard. But whilst I'm talking about correcting PCB patterns, I just want to make sure of the pinouts of this relay are correct. Like, it should be common, normally open, normally closed, but I need to verify that, because if this is a relay I'm going to be using, the layout's got to be right. Now I'll use my multimeter on continuity. Nothing there, something there. So what I'll do is I'll just apply a small voltage, 8.5 volts, 9 volts from a battery should be fine, just to make the relay engage. It's 12 volt, but usually they will turn on with as little as 7.5 volts. Well, that's the theory anyway. Yes, it does. So that should now have no continuity. Right, so that is definitely correct. So it is definitely common. Normally closed, normally open. And the DC resistance of the coil is more closer to 260 ohms. Okay, after screwing around for a bit, I've got the circuit built up over here, and I thought, Well, I had to build the actual power supply section of that circuit as well, and then I thought, well, no I don't, I can just use this power supply here. Because I am actually going to redesign the power supply with the muting relay on it, so I'm not going to be using this power supply anymore. So I got my two transformers hooked up to the supply. I've got a better plug arrangement here, so I'm just going to verify that the supply still works before I connect the circuit to it. Indeed it does. Both LEDs are lit up, so both sides are working. This yellow wire hanging down here is my AC off the secondary side of the transformer. Right now I'm starting with the 470 ohm resistor in there. If the relay doesn't pull in, it doesn't pull in. Right, so after verifying that there's nothing shorting, which it's not, and that everything is wired correctly, see what happens. Oh, well, the LED lit up. I did hear the relay click, but I don't know if it's actually fully engaged, so sounds like it though. Okay, I've got my multimeter in continuity mode across the contacts, and I'll just plug it in again. Yeah, it works. It's about two and a bit seconds, which should be enough. At least the LED is lighting up and I didn't blow it up. I don't know if you guys can see that. It is actually illuminated. The circuit does work, and I don't have to modify the timing of the circuit. It's perfectly fine as it is, and it works fine with that relay, even though the coil resistance is about closer to 280. Okay, let's plug it in again. We are up to 8.68 volts. So, okay, as for this transistor, it is slightly hot to the touch, but it's not overly bearingly hot. It is hot, but it's not smoking or anything, and I've got 10 odd volt across the coil, which is perfectly fine. And as for that transistor getting hot, I've built this circuit up as a kit several times and I've never had a transistor fail, even if it is getting hot. Alright, I've left the circuit run and walked away from it like a real world situation here. That is quite hot. So next thing I'm going to do is I'm going to measure the voltage drop across that 470 ohm resistor just to figure out how much current the relay is actually drawing. There is, I'm not worried about the minus part, there's 22 volt and falling going across that resistor. So I'm going to say 21. Okay, so using Ohm's law, I know the voltage. I want to find the current, so that's the voltage divided by the resistance. So it's now currently sitting around about 20 volt mark, divided by 470, 42 mA. So at that current, it's well within what the transistor can handle. The transistor is rated for about 80 mA, I think it is. So it's only half the current going through that transistor. As for it getting hot to the touch, that's probably more due to the fact that it's handling a lot of ripple. There's quite a bit of ripple going through that transistor. So a power transistor here probably would be a better choice, but as I say, this circuit isn't broke. It has worked in the past with that current transistor. This is a BC546 now instead of a 548. Irrespective of that, this circuit has actually worked fine for years. It's just not the greatest design, I suppose. You can actually buy clip-on TO92 heatsinks anyway, but they're exceedingly expensive. They're like about nearly $7 each, which is quite expensive. However, I'm going to leave it as it is because, as I say, it's not broke. It does work. I mean, I am putting through a slightly higher voltage than the original design was designed for. They had a 28028 transformer, or 56 volt center tapped, which gave you 40 volt at the end of the day as DC. So there'd be more like 18 or 19 volt across this mute circuit, but no, it works. Anyhow, I'm going to have to update my layout to accept the
Full bridge rectifier.
yeah, because it's wrong. And there is my board layout there, and I've corrected the
Full bridge rectifier.
I'm going to stop doing that now. I've corrected the full bridge rectifier and put it back to the original footprint I had to start with. Moved some stuff around. I've verified that the relay is the correct footprint and the pinouts are wired correctly, which they are. So now I'm ready to re-export the Gerber and see if I can actually get the bloody thing uploaded to PCB way, because I'm going to put that 1 watt amplifier PCB on hold for now and concentrate on this. So I go File, Plot, which is really non-intuitive. Make sure the edge cuts is selected, front mask, back mask, front silk, back copper and front copper are selected. Click on Plot, which doesn't really make sense. Then I have to generate the drill file. So drill file goes to the same folder. That's that. The board is now exported as a Gerber, and so all I have to do is go in here, re-zip the contents to that, and I'll just give it a much more meaningful name. I'm calling mine the AEL 480 just for nostalgia. And I'll go to the PCB website and see if I can modify the Gerber that I've uploaded. I hope I don't have to, like, you know, delete the Gerber that's there and start again. Whatever. No, it didn't let me update the Gerber. I had to delete the order and re-upload the order. Right, it has actually finally been approved. It took about 20 minutes, but it's been approved. 2-layer board, 110.5 by 69. Nice. 0.8. And blue solder mask, like I like. I'm ordering 5 of them. So that's the front view of the circuit board, and that's the rear view of the circuit board. Looks pretty sexy. Again, the camera doesn't do the color justice. It's a little bit deeper blue than that, but that's alright. So now I need to go to the payment section and work out. It actually got reduced from 27.26 to 24.14. Changed. It says for the reason for the change, the width 89.85 was changed to 69.8. Oh, I put the wrong measurements in. Okay, so they gave me a discount because, well, if it had been 89.85, that's what it would have cost. That makes sense. So now I need to proceed to the checkout to actually calculate what the total cost is. Okay, currently 88.59, but that's because of the shipping. Change that to credit card, and I will change that from DHL to Global Standard. 32.74. Not bad. That's almost $50 AU, and the price hasn't changed from last night when I did it, so I don't need to change the figures. So $32.74 US dollars is roughly $48.96 Australian, so you might as well say $49. Okay, that's, yeah, borderline expensive, but okay. Alright, so I can go ahead and pay for that now. And the other good thing is you can actually share and sell your PCB so other people can buy it on PCB way, which is what ElectroIndia did in the first place, and I don't see a problem with that. And I might actually share it and sell it because I'll get 10% commission on all board sales, and also 10% commission on any assembly that they do for the customer, because they can assemble the boards too for $30 US. So I'd receive 10% of that, which is $3 US. So anyway, I'm going to leave this video here. I'm going to go ahead and pay for that now and wait up to a month for it to come here, and then we'll see back again later when I finally receive the PCBs. Anyway, I'm the Astro 30. If you enjoyed this video, please remember to rate, comment and subscribe below, and you can always become a Patreon member for as little as $1 a month. That'd be great. I'm doing all this work for entertainment value for you guys. And you can also follow me on Facebook. The links are in the description as usual. Anyway, this is the Astro 30 saying happy PCBs! Yay!